So good morning, everyone. Today I will talk to you about the technological watch group of GENCI, and more precisely on the KNL assessment that we made within this group. And so I will give you a brief presentation of GENCI, the group, and of course the results that we obtained on the platform. And first of all, I will thank all our partners that help us within this group, because without them we couldn't do what we have done within this project. So I will name all of them: Maison de la Simulation, CNRS, INRIA, CINES, IDRIS, TGCC, Groupe Calcul, and CEA. Thanks to all of them. A few words about GENCI. So does anybody do not know GENCI here? No? Okay, so very quickly, we're in charge of the national HPC strategy, and we have partnership at regional levels. We represent PRACE in France, and we promote the use of supercomputers in industry. So it's not only in the academic world, I would say, but we also promote the HPC for industry. So about the watch group, I told you we performed a lot of experiments on various kind of stuff. So the idea of this group is to anticipate what is coming up, to anticipate the exascale architectures, to organize code modernization, and to share the expertise that we can produce. So in order to do that, we deployed two first machines. One is a Bull Sequana platform, which is based at CINES. So you have seen the Sequana platform, which has been presented by Olivier. And so within this platform, we have 48 nodes, 48 KNL nodes, for a total of 146 teraflop of peak performance. And on the other hand, we also have an IBM Open Power platform. So maybe you are not familiar with the Open Power platform, but the idea is that you have Power CPUs, so IBM Power CPUs, and linked to those CPUs, you have GPUs, NVIDIA GPUs, which are P100. And with 12 nodes, we reach a peak performance of 254 teraflops. So as you can see, the performance per node is much more important on an Open Power node than on a KNL node. Those platforms are available through the preparatory access process. So if you want to have access to one of those platforms, you can get in touch with me, or you can go to idari.fr. And this process is a French process, but maybe if you have something interesting to propose, or if you want to work with us, please feel free to contact me. And on top of that, we also have a tight collaboration between the developers, the vendors, and the HPC centers. So in order to have performances, to use the platforms, we organized a lot of workshops. We really wanted to talk between the vendors and the users, and I think we really managed to do that. So a few more words on the platform. I told you we have 48 nodes, KNL nodes, 24 in quad cache mode. So as Matt told you what is quadrant mode and cache mode for the memory, and 24 in quadrant mode for the processor, and flat mode for the memory. And those nodes are interconnected thanks to EDR interconnect. The quadrant mode is used for both partitions. At the beginning, we had big issues to have performances using other modes, so we remained in quadrant mode, and we have good performances, so for us that's okay. And as I told you, we have high-level support thanks to Atos and Intel. So today I will present you a brief summary of the performances we got on those applications. And I will go maybe deeper on one or two applications. So what you should know is that we have been working with 18 real-world applications. We have two applications which are focused for GPUs. So I have no numbers for them today, of course, because KNL is not GPU. We have one OpenCL application which couldn't run on the KNL because OpenCL support is not mature. Or, I mean, it's not that it's not mature, but it produces AVX2 when we want to have AVX 512. so it's not efficient. And we have 15 standard applications and 2 withdrawals. So I have results for 13 applications plus NAMD because we had results thanks to Atos and NAMD, so I can present it to you today. So here is the overall performance on those applications. The comparison is made between a Broadwell architecture, so 2 times 14 cores at 2.6 gigahertz, and the KNL. So the KNL is 7250, it's 68 cores at 1.4 gigahertz. So as you can see, for more or less all the codes, we have at least the same performance between Broadwell and KNL. Of course, not all of them. We can remove AVBP, but work is in progress to improve. Gisela, QMC Chem, and those 2 as well. But the mean value is quite good. We have times 1.3 for those 14 applications. And what I really wanted to point out is that, okay, the performance increase is not amazing, but the energy efficiency seems to be amazing. In fact, what we did is that we computed the TDP ratios between the Broadwell and KNL, and we can guess that we have an energy gain of 1.8 for using KNL instead of Broadwell. So for us, it's a very important result because it's good to have performances, but if you can reduce your energy impact by 2, it's also a very, very good result. So just a few words on the memory mode. So Asma presented you the flat mode and cache mode. She told you that the flat memory is more efficient, you have higher bandwidth and so on. For us, on our real applications, in fact, what we had is that for almost all of them, the cache mode was better or had the same performance than the flat mode. So in fact, we more or less decided to use only cache mode for the applications. And on top of that, this will not require the user to add, to change his code and to add lines in his code to allocate manually memory into the MC DRAM. So for us, the cache mode could be the solution to use this kind of architecture quite efficiently, to have good performances and to be more energy efficient. So this was for the node-to-node comparison. I have a few slides on the scalability for 2 applications. So the first one is DYNAMICO. DYNAMICO is dynamic kernel for climate applications. So as you may have seen on the last slide, the speedup node-to-node is 1.86. On 16 nodes, the speedup is 1.61. So that means the scalability is not as good on Broadwell than on KNL because the speedup is a bit less on 16 nodes than on 1 node. We have a use of the vectorization, but it's not at its best. So the speedup of using vectorization versus not using vectorization is 1.43. So maybe we have some troubles with the bandwidth or so on. And we have no impact of the flat mode. So what I can tell you, thanks to this slide, is that this machine scales well, but not as well as what we have on a Broadwell machine. And what is interesting is that we performed 1 more test. So at the beginning, we thought maybe this scalability issue could be a latency issue, because as you know, the KNL runs twice slower as the Broadwell, or almost twice. So we thought maybe the latency of the KNL makes the code not be as scalable as what we have on the Broadwell. So we reduced the frequency of the Broadwell. So that's what you can see on the yellow curve. But on the Broadwell, the code is still more scalable than on the KNL. So it doesn't come from the latency. So a lot of time when you hear about scalability on KNL, people are telling, okay, the scalability is not as good on KNL because of the latency. It's not totally true. Here is another application. So this time it's still it's still about weather. It's atmospheric model. This time we see the impact of the scalability, and we see that the speed up is not as good on a KNL machine than on a Broadwell machine. But here we know that the issue comes from the test case. In fact, the mesh is divided using MPI processes. So you create subdomains. If you create subdomains on Broadwell nodes, you will have 28 cores per node times 16 nodes. So you have something like, I would say, 500 subdomains. On the KNL, you have more than twice more cores. So that means maybe you will have three times more subdomains. So if you have more subdomains, you have more overhead in terms of computation, you have more overhead in terms of communications. And so that can explain why we have a better speed up using a standard machine, I would say, than a KNL machine. So in this slide, I could recommend you to think about your code and to think about using OpenMP within your code. Because OpenMP will reduce the number of subdomains. You will not have overhead in computation. You will not have overhead in communication. And that could really improve the curve. So this code has been ported to OpenACC. And we have not performed any tests on OpenACC yet. But maybe if we use OpenACC on KNL, because it's working, maybe we could have a better curve and have a better scalability on this part. So that's all for the scalability. I wanted to show you one slide, but Alfredo Butari, which is porting the code, will present a bit more in detail this afternoon its application. But this application is interesting because that's one of the applications that we could measure in terms of energy. So we have five test cases and speed up, which is, so the difference is the speed up is computed between Broadwell and KNL. And the speed up is about 1.4 for 4 test cases and about 1 for 1 test case. And what we can see is that we computed the energy, and the energy gain is about 1.9 for the 4 test cases with a speed up of 1.4, and about 1.45 for the remaining one. And this is interesting because what we have here is more or less exactly what we computed using the TDP ratios. So earlier I told you that a KNL is 1.8 more efficient than a Broadwell. And thanks to this slide and those results, I can tell you a bit more that a Broadwell is a KNL is 1.8 more efficient than a Broadwell. It's not sure. For sure, we have to compute those numbers. We have to perform some tests on all the applications. But I think that's a good mean value. So I wanted to add a few words about the PRACE efforts. I don't know if you are aware of the UABS benchmark suite, but this suite has been ported to accelerators, or is being ported to accelerators. And so we were really pleased to help this suite. And so thanks to the FRIOUL machine, we already have results for benchmarks in this suite on GROMACS, NAMD, QCD, and SpecFun 3D. And the Wesson machine that I told you about, so the Open Power machine, has also been used, and we have also results on this machine. So just a few words about the PRACE benchmark suite. The next steps. So the next step is really to have the time to solution and the scalability for those applications. But on top of that, we really would like to add the energy to solution. And how do we do that? It's quite easy. We have a PCP program, so you are all aware of. And we have 3 machines. We have the Davide machine, which is on the Open Power platform. the FRIOUL PCP machine at CNES, which is a KNL platform, and an FPGA platform built by Maxeller, which will be available in Germany. And so those codes will be run on those platforms. I would say those codes will be run on almost all those platforms, because as you can see, it's quite difficult for the developers at the moment to say, okay, I will run on FPGA, because it requires a lot of effort in terms of application porting. So it's still an issue at the moment to make people work on this machine. So to conclude, what I would like to tell you about the KNL system is that it's really easy to use. You have a good speed up after only a few hours, few days work. We have quite good results at scale, but really think about OpenMP. If you want to go at scale, at very large scale, you have to reduce your communication, you have to reduce your computation overhead. So think about OpenMP. It's very energy efficient. I told you about 1.8 as a mean value for those 14 applications. And to continue working on this path, to continue working with the KNL, you have a lot of PRACE activities. So as you may know, the PCP system and FRIOUL, which was here for the technological watch group, are available through PRACE. We have already large-scale system. So we have Marconi at Cineca, which is a 10 petaflop machine based on KNL. We will have Curie's successor in France. So its name is Irene. And it will also benefit from this technology. So 1/3 of the machine will be KNL. And so if you really want to use this architecture, don't miss the call number 16. So there is a PRACE call. The close of the call is 21st of November. So don't miss it. And the start of allocation is 3rd of April 2018. So just for your information, Curie's successor will be available at the beginning of mid-2018. So if you apply for this call, you will probably be able to work on KNLs on Curie, but also Skylakes. So that could be a very good idea for you to test those architectures. Thank you for your attention.